Hello and welcome back. Now that we've gotten done what the graphs of sine and cosine look like, we're going to investigate how those will relate to our other 4 of our 6 basic functions. So we're going to be looking at graphs of tangent, cotangent, cosecant, and our friend secant. One little skill we're going to want to remember, or a property we're going to want to remember: tan theta is equal to tangent of theta plus k pi k in z. So any integer. So this tangent graph, once we have the first interval drawn, we know it will just keep repeating over and over again. Also recall tangent theta, sine theta over cosine theta. Now, since division by 0 is always undefined, this graph is going to be undefined anywhere cosine theta is 0. Some places where cosine theta is worth 0, theta is plus or minus pi over 2, 90 degrees, plus or minus 3 pi over 2, so 270, and really any odd pi over 2. So we have places where this is going to be undefined. Now let's let y equal tangent of x. So x is sort of acting like our theta used to act. So tangent of x is our y value. So we'll start at negative pi over 6. Since we know negative pi over 2 is already at undefined. So 30 degrees, but in the negative direction. So our cosine is still root 3 over 2. Our sine is at negative 1/2. The 2's drop, so negative 1 over root 3, which is negative root 3 over 3. So just hit this top and bottom with root 3. Negative pi over 4. So a 45-degree angle, but in Q4. Sine is negative. Cosine still positive. And that'll simplify down to a negative 1. Negative pi over 3. So now we're talking 60 degrees. The sine is still a negative, but we're up to root 3 over 2 for the sine, and 1/2 still positive for the cosine, so negative root 3 for that guy. Now if we look at places where sine is 0, well, sine of, we'll just go in the middle, 0. Sine of 0 is 0. 0 divided by 1 is 0. And pi over 3. So the cosine is unchanged. The sine just flips over to positive. So that makes that a root 3. Similarly with pi over 4, cosine had the same sign as before. Sine flipped signs. We're at a 1, and pi over 6. Oh. Pi over 6 would be positive root 3 over 3. Now, we're not going to necessarily draw every single one of these out every single time. It's just a good idea to sort of start getting to know where some of these are located and some rough ideas of what's happening. So let's see, we know from negative pi over 2 to pi over 2, those two values, we won't have a point on this graph. What we do have, we've got the origin. Yeah, let's see, so pi over 6, we're sort of the closest in, and that is negative root 3 over 3, which is about negative 0.58. Negative pi over 4, so halfway to the negative pi over 2, we're at a negative 1. Negative pi over 3, approximately negative 1.73. And we have similar points happening over here. So it's a little bit hard to see the curvature of this. So let's start seeing what's happening close to the edge. So in the calculator, if I try out the tangent of 99 pi out of 200, so pretty close to pi over 2, but just a shade to the left of it. 100 pi over 2 would simplify to just pi over 2. We're a little bit smaller than that. And we get approximately 63.6567, blah, 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 it keeps going. If I try the tangent of 999 pi over 2000, again, very close to pi over 2, but not quite there. And now we're at approximately 636 and 619, blah, 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 keeps going. And if you try one more, 9,999 out of 20,000 pi. Now we're again about an order of magnitude larger, 6,366 and change. So the closer I get to pi over 2, as I mentioned, closer and closer, these are getting closer and closer to infinity. So this is really, you might recognize that concept as an asymptote. So we start getting very close to positive infinity the closer we get to pi over 2. Similarly here, if we just flip the sign on these guys, we'll start getting closer to negative infinity. And remembering that this pattern repeats between pi over 2 and 3 pi over 2, the next place where we're undefined, and 1 pi unit away, we have that same sort of pattern emerging. So this will just repeat forever. We have an infinite number of these nice pretty curves, these tangent lines. That brings us to our friend the cotangent next. So cotangent, recall, is cosine theta over sine theta, or cosine x over sine x, whichever you'd like to think of. So this one, recall, is undefined when sine of theta or sine of x, whichever variable you're using, is equal to 0. So sine theta equals 0 at well, 0 for starters, pi, and it doesn't matter if we rotated clockwise or counterclockwise, so plus or minus pi, plus or minus 2 pi, that's the same as the 0, plus or minus 3 pi, plus or minus any k pi. So notice these are still pi units apart, so we still have this repetition at any k pi, just like the tangent did. So this time our y-axis is one of our tangent lines. So we'll see what's happening between just 0 and pi, and we know that that's going to then repeat. So at pi over 6, you'll recall that cotangent and tangent are reciprocals of one another. So at pi over 6, we had root 3 over 3, so its reciprocal would be root 3. Pi over 4 is still going to spit out a 1, since sine and cosine are equal, and we're in Q1 on the unit circle. Pi over 3, we're looking at the root 3 over 3. So remember, cosine of 60 degrees is a half. Sine of 60 degrees is root 3 over 2, so you get 1 over root 3 and rationalize it. If we look at, say, pi over 2, 90 degrees, cosine is 0, sine is 1, 0 over 1 is 0. And then we'll just add, so pi over 2 plus, we'll add just 30 degrees to it. So that is 3 pi over 6 plus 1 pi over 6, 4 pi over 6, or 2 pi over 3. And that would spit out a negative cosine, so we have negative root 3 over 3. If we do 3 pi over 4, so 1 pi over 4, 2 pi over 4, 3 pi over 4, sine and cosine have the same absolute value but opposite signs, so that'll give us a negative 1. And at 5 pi over 6, so pi over 2 plus the 60 degrees. Ooh, my apologies, I didn't need to close that up quite yet. Negative root 3 is our solution there. So let's start plotting some of these. So we're undefined at 0, but at 30 degrees we have root 3, that's about 1.73, so around 1 3/4. Pi over 4, we're at a 1. Pi over 3, we're at 58 hundredths, about a half. Pi over 2, so recall this is our point that's at pi. Pi over 2, we're at 0. And then we start heading down this way. This guy should be down here, and about 1 3/4. And then the same thing is going to happen. We're going to approach those undefined values, so an asymptote again. So here's our 2 pi, and that pattern is going to repeat for us. And the same thing will happen over here, negative pi. Now the same rules apply that applied before as far as shifting, stretching, compressing, things like that. So if we have, and this will hold for the tangent or the cotangent, y is a tangent omega x plus b, or for y is a cotangent omega x plus b. So a is still our amplitude. Just multiply your outputs by the a value on the basic one. Plus b shifts us up or down, and omega, since it's inside with the x, that's controlling horizontal stretching or compressing, and the period on that then would be pi over omega. So usual rules. Alright, so we'll go through the changes on, we'll do y is, let's say, -3 cotangent of 2x plus 1. Now we're just going to graph some key points. We're not going to make the huge tables like before. I know your calculator can spit out a table of decimal approximations. That's not really what we're interested in here. So we're just going to use our graphing properties. So I'll start with y is the cotangent of x. And in the early stages, I'm just going to draw maybe 2 or 3 cycles of it, and we just kind of build it from there. So the basic cotangent one, we know we have asymptotes at 0, pi, 2 pi, etc., -pi, -2 pi. And we know in the middle, we hit the x-axis each time. And there's our basic curve. We know at pi over 4 we should be at 1. And at 3 pi over 4 we should be down here at -1. And we know at pi over 2, of course, we're at 0. So we'll just do those 3 key points and kind of trace what happens to those, and then just kind of draw quick rough sketches of the rest of our here. Ooh, I kind of leaned in a little too hard there on the -pi to 0. Okay, so we have a rough sketch of what's happening there. So then as far as what's happening with it, the most critical one to take care of next would be anything that's affecting the period of the function. So this is multiplied by 2. Remember, it's inside, so inside with the x, it works sort of the opposite of what we think. It's not going to double the period, it's actually going to cut it in half. So our period goes from pi to pi over 2. So we're just kind of bringing those in a little bit further. So we still have an asymptote at 0, but now we have an asymptote that used to happen at pi, now it's happening at pi over 2. And that should make sense. If you plug pi over 2 in here, 2 times pi over 2 is pi, cotangent of pi, undefined. So that means I can get a couple cycles in going this time just out to pi. And we'll do that in the other direction as well. So it used to be at pi over 2 where we were at 0. Now at pi over 4 we're at 0. So it used to happen at 3 pi over 4. Now that's happening at 3 pi over 8, half the distance. And what used to happen at pi over 4 is also happening again at pi over 8. So there's our sort of more detailed first one, and the rest of them we're just going to kind of loosely sketch in the idea. So next we'll do the -3. Yeah, and we'll just scale that by halves. So there's a half, there's 1. Half is now 1, 1 is now 2, 1.5 is now 3. So remember, anything out here that's a times f of x, just take your old y values, multiply it by a. So our asymptotes haven't moved. So they're still at pi over 2 and pi, and negative pi over 2 and negative pi, and counting by pi over 2 is forever. The zeros are still glued down at 0, so all these midpoints are still on the axes, except instead of going to 1 at pi over 8, I'm going to go to 1 times -3, -3 at pi over 8. So we have our pi over 8, -3 down there. We already talked about pi over 4 still being 0. 3 pi over 8, my output used to be -1. -1 times -3 is now +3. So we had a vertical stretch. And we repeat that pattern. Lastly, the +1. I'm going to let you all sketch that on your own. All of these points would be moved up 1 unit. So the 3 pi over 8 on the last graph will be at 4. Pi over 4, instead of being at 0, would be at 1. Pi over 8, instead of being at -3, it's at -2. And that pattern continues. All right, so that's our cosine, or I'm sorry, our cotangent and our tangent. The cosecant and secant, we basically just base those on the sine or the cosine. All right, so we'll start with, we'll just build a secant one. We'll do y equals secant of x. Secant is based on cosine, so our y1 is cosine x. So remember, this one is a cycle that is 2 pi in length as opposed to pi in length, like the tangent and cotangent had. So one full lap around will bring us to the 2 pi, and we'll do two cycles of it, so we'll go to 4 pi. Alright, so here's our pi, here's our pi over 2, 3 pi over 2, and that'll give us enough to sketch a good graph. And we'll make the ones, we'll stretch them out a little bit. Okay, so cosine of 0 is 1. Cosine of 90 degrees is 0. Cosine of 180 degrees, negative 1. Cosine of 270 degrees, we're back at 0. And cosine of 2 pi, we're back at 1. So here is our cosine graph. And we know that that will happen again. So here's our 3 pi. We should be down here at negative 1. And so on. So cross at the midpoint there. Cross at the midpoint there. And we're back up here. And that keeps going. And that keeps going. Well, remember, 1 is its own reciprocal, so I'll do the secant, we'll just do this in blue here. So 1 is its own reciprocal. Each of these points appears on both y1 and y equals secant x. Negative 1, also its own reciprocal. 0 does not have a reciprocal. Now let's talk about the values between 0 and pi over 2 here. If you exclude the endpoints of 0 and pi over 2, these are all proper fractions. They're bigger than 0, smaller than 1. The reciprocal of a proper fraction is an improper fraction. So these are just sort of flipping over. And notice, as we head towards a point that would be undefined, that's the idea of an asymptote. Three pi over 2, again, the output is 0, so the reciprocal doesn't exist. It's undefined. Negative 1 is its own reciprocal. And then we start heading this way. Again, 0 doesn't have a reciprocal. Turn that into your asymptote. And there's our new function. So this in blue is what the secant would look like. And we can do all this stuff with secants and cosecants that we could do with any other graph that you've worked with since your college algebra days. So we'll do one last quick one. We'll do y is equal to 2 cosecant of x. So we'll start with, this one is based off of a sine graph. So y equals sine x. We'll start there. So we'll make this a 1 and a negative 1. And again, we'll just do maybe 2 cycles of the sine. So here's our 2 pi, here's our 4 pi, here's our pi and 3 pi, pi over 2, 3 pi over 2, 5 pi over 2, and 7 pi over 2. Okay, so sine of 0 is 0. Sine of pi over 2 is a positive 1. Sine of pi, we're back to 0. Sine of 3 pi over 2, we're at negative 1. And sine of 2 pi, we're back to 0. So that one, hopefully you've done enough practice problems that you can do the sine graph kind of in your sleep at this point. So here's just 2 quick cycles of the sine function. So next up, I guess in blue here, I'll do y equals cosecant of x. Same idea of what we did with the secant. 0 does not have a reciprocal, so those will end up as asymptotes. 1 is its own reciprocal, so that means we're headed up here. Negative 1 is also its own reciprocal, so we're down here. We just have proper fractions turning into improper fractions, either in positive territory or negative territory. Alright, so there's a couple cycles of the cosecant graph. So then the last one, I guess red will do it. 2 cosecant x. There's nothing magical about this being a cosecant as opposed to a parabola or any other shape that you've graphed. This just means take your old y values and multiply them by this number. So 1 times 2 is 2. Negative 1 times 2 is negative 2. 1 times 2, again, is 2. So just a vertical stretch, and our starting point changes on each of those. All right, so there is our ideas for the secant and the cosecant. So 6-5, I would recommend 3 to 39 if you're doing the problems out of the text, or I'll put some my math lab ones up as well that you can try, whichever you prefer. If you have questions, please come up, see me on either email or Zoom, and stay safe out there, everyone.